Have you ever wondered what holds the universe together? The invisible threads that bind galaxies in vast, silent webs. Out there, in the dark between stars, most of what exists cannot be seen. No light reflects from it. No telescope captures its glow. Yet its pull shapes everything. The spin of galaxies, the dance of clusters, even the fate of cosmic expansion. We call it dark matter, but that name hides more than it reveals. Is it made of unknown particles? Something deeper, woven into the fabric of space itself? Tonight, we'll explore how scientists chase a shadow that outweighs everything we can see. If quiet curiosity is your orbit, a light tap on like and subscribe keeps you close to ours. Settle in the Dark has much to show. For almost 100 years, astronomers have been watching galaxies move in ways that make no sense if light is all we can trust. The stars hold together when gravity alone should let them drift apart. Entire clusters of galaxies seem to move as though something invisible is guiding them. Every clue has pointed toward the same quiet truth. There is more out there than what light can show us. It began with small, careful observations, and it led to one of the greatest mysteries in science. Picture the night sky not as a flat field of stars, but as a vast ocean where galaxies drift like islands. They move, but they do not fall apart. Something unseen must be holding them in place. In the calm decades between the two world wars, telescopes were still guided by hand, and photographs of the heavens took hours of exposure. In that patient era, a Swiss astronomer named Fritz Zwicky began studying a cluster of galaxies far beyond our own. It was called the Coma Cluster, a massive collection of thousands of galaxies, each one filled with billions of stars. Together they formed a bright, slow dance in the darkness of intergalactic space. Zwicky measured how fast these galaxies were moving. The numbers shocked him. They were racing through space far faster than they should. According to Newton's law of gravity, the visible matter in those galaxies, stars, gas, dust, wasn't nearly enough to keep the whole cluster together. The galaxies should have drifted apart long ago, scattered like sparks from a fire. Yet they hadn't. They were still bound, still circling within the cluster's unseen grip. The math told a strange story. The Coma Cluster appeared to weigh hundreds of times more than what could be seen through a telescope. Zwicky needed a name for this missing ingredient. He called it Dunkel Materia, or dark matter, not to be poetic, but simply to describe what the eye could not see. His calculations came from what scientists call the virial theorem, a simple principle connecting how fast objects move inside a system to how much mass that system contains. If galaxies move faster than they should, then more mass must be hiding somewhere, creating the extra gravity that keeps them in orbit. Gravity, after all, obeys one rule: the more mass you have, the stronger your pull. Zwicky's observations implied there was a vast amount of hidden mass providing the glue, but few took him seriously. He was brilliant, but famously difficult. His sharp comments and lack of patience didn't win him many friends. Still, his math was solid. The Coma Cluster truly behaved as if it carried an invisible weight. The idea of missing mass was unsettling. At that time, the universe was thought to be made only of visible things: stars, planets, gas, and dust. The notion that most of its matter could be invisible felt absurd. Maybe, people thought, Zwicky had made a mistake, or maybe the light from distant galaxies was bending in ways not yet understood. It was easier to assume a flaw in the data than to believe the universe itself was hiding something so large. Yet the numbers kept pointing in the same direction. The galaxies in the Coma Cluster were moving too fast to be explained by visible light alone. Even if every star, cloud, and glimmer of gas were added together, it still wouldn't be enough. Something unseen had to make up most of the cluster's mass. Imagine floating above the Coma cluster, looking down at thousands of galaxies, shining like tiny lanterns. Between them lies darkness, not empty, but full of invisible weight, a web of something that binds each galaxy in place. If that hidden mass were removed, the galaxies would scatter into the black, drifting apart like sparks fading into night. Zwicky's discovery planted a seed of doubt in the bright picture of the universe. For the first time, scientists had to consider that the visible cosmos, the glowing stars and colorful nebulae, might just be a thin surface over something much larger. He couldn't know it then, but his lonely calculations were the first cracks in our understanding of the universe's structure. Behind the light, there was a hidden architecture waiting to be uncovered. It would take decades for others to notice. Nearly a century later, we are still trying to understand what Zwicky stumbled upon. It was not a trick of measurement or a misunderstanding of physics. It was a truth so deep that it would change cosmology itself. The visible universe was not the full story. The galaxies lighting up the night sky were only decorations on a far greater structure. There is something oddly comforting in that thought, that even in darkness, there is structure and balance. The Coma cluster did not need more stars to stay together. It needed the quiet weight of the unseen, gravity born from something that never glows, never calls attention to itself, but holds everything steady. Zwicky didn't have the tools to see what this something was. He only had the courage to say it must exist. His data didn't reveal a new kind of star or planet. It revealed a new kind of ignorance, a reminder that the universe still held secrets beyond our reach. And as time passed, astronomers began to see the same imbalance in other galaxies too. The whisper that began in the Coma cluster grew louder, echoing across the cosmos until no one could ignore it. What Zwicky saw was not an error, it was the first sign of a hidden order shaping the universe. The whisper had become a pattern. By the middle of the 20th century, astronomy was changing. New telescopes and instruments allowed scientists to measure the motion of individual stars within galaxies. Among the quiet revolutionaries was an American astronomer named Vera Rubin. She was calm, precise, and endlessly curious. She loved the night sky not for its mystery, but for its steady rhythm, the language of data, the elegance of orbits, the patient truth of numbers. Rubin focused on spiral galaxies, those graceful disks that look serene from a distance. Inside, though, they hide a puzzle. When a galaxy spins, its inner stars, those near the center, should move faster than the stars at the edges. Gravity weakens with distance. The farther you are from the center, the slower your orbit should be. It's the same rule that shapes our solar system. Mercury, close to the sun, whips around it quickly. Neptune, far away, takes over 160 years for one lap. The rule is simple. Farther means slower. But when Rubin and her colleague Kent Ford began measuring how fast stars moved in real galaxies, the rule broke. They used the Doppler shift, the tiny change in a star's light as it moves toward or away from us, to track their speeds at different distances from the center. The results were consistent and shocking. The stars on the outer edges were moving just as fast as those near the middle. When the data were plotted on graphs, the rotation curves didn't fall off like a hill. They flattened out, stretching straight across the page. It was as if the outer stars had decided to ignore Newton's law. Galaxies, it seemed, were great at ignoring instructions. Rubin described her findings with care, never overstating, never dramatizing, but the meaning was clear. Galaxies should have torn themselves apart long ago, if only visible matter were holding them together. Yet they hadn't. Something invisible was providing the extra gravity, something several times more massive than all the stars combined. Whatever it was, it didn't shine, didn't collide, and didn't behave like normal matter. It surrounded each galaxy in a vast halo, stretching far beyond the visible edge. To picture it, imagine a record player spinning slowly in the dark. The bright dots near the center whirl fast, but the faint ones near the rim move just as quickly, kept steady by an unseen hand. Gravity is the music, and dark matter is the hidden rhythm keeping time. Rubin's data came not from one galaxy, but from many, from small dwarfs to giant spirals. In every case, the pattern repeated: flat curves, fast outer stars, hidden mass. What began as one anomaly became a rule of nature. At first, the idea met resistance. Some thought her measurements must be wrong. Others suggested gravity itself might need rewriting. But Rubin was relentless. She refined her methods, tested new galaxies, and built a mountain of evidence so consistent that no one could ignore it. The galaxies were not misbehaving. They were revealing the hidden structure of the universe. Rubin's work was remarkable not only for its precision, but for her calm way of presenting it. She didn't frame her findings as a cosmic shock. She treated them as another step in understanding, another layer of truth the universe had quietly waited for us to notice. She once said, "We are still groping for understanding." It wasn't a confession of confusion. It was a statement of wonder. Her results carried huge implications. If every galaxy needs an invisible halo of dark matter to hold itself together, then dark matter must be everywhere. It isn't rare or local. It fills the cosmos. The bright stars and glowing nebulae are just the thin frosting on an invisible foundation. Rubin never claimed to know what dark matter was. She only showed that it must exist. Her steady determination reshaped modern astrophysics. The universe was suddenly heavier, stranger, and far more beautiful. For every glimmer of light, there was an ocean of unseen mass, making sure it stayed in place. Her discovery also said something profound about science itself. Sometimes, the universe doesn't shout its secrets. It whispers them through patterns that refuse to fade. A flat line on a graph can be as powerful as an explosion if we have the patience to listen. Rubin's galaxies continued to spin, calm and constant, as if reminding us that light is not the only way to see reality. Behind every star is the gentle pull of the invisible. And behind every discovery is someone who noticed when the numbers didn't fit. When Vera Rubin passed away in 2016, astronomy lost a brilliant mind and a spirit of quiet curiosity. Her work confirmed that dark matter wasn't just a theory, it was a cornerstone of our understanding of the universe. She showed that even on the grandest scale, progress begins with something small. A measurement that doesn't behave, a graph that stays flat. Her galaxies keep their rhythm. They turn, unhurried and sure, guided by invisible hands. Each one, a reminder that the universe's greatest forces are not always the ones we can see. Light shows us beauty, but the dark reveals truth. And in that balance, between brightness and shadow, lies the quiet heart of the cosmos, spinning endlessly through the night. Gravity leaves nothing untouched. It's the quiet accountant of the universe, keeping perfect records of every hidden weight and unseen mass. You can hide from light, but not from gravity. Even the invisible must leave a trace. A planet, a star, a black hole, or a cloud of particles we can't yet name all bend space itself, pressing into the fabric of the cosmos and changing how things move around them. Einstein's general theory of relativity showed that gravity isn't a pulling force that stretches across space like a rope. It's the shape of space and time together. Every object with mass curves that shape, creating dips and valleys that other objects roll into. A star or planet makes a deep hollow. A pebble makes a tiny dent. Even you, right now, are bending space around yourself, though only by the smallest amount. Light, which always follows the straightest path through space, doesn't escape these curves. When it moves near something massive, its path bends. It doesn't change direction because it wants to, but because the road itself is warped. That's why, even though dark matter doesn't shine, we can still tell where it hides. Its gravity bends the light coming from galaxies behind it, stretching and distorting their shapes. Sometimes, the effect is so strong that the background galaxy appears more than once, like a reflection in a hall of mirrors. Astronomers use these distortions, this gravitational lensing, to map where the unseen mass lies. By studying how the light bends, they can trace the invisible terrain of the universe. It's a little like watching ripples spread across a pond. You might not see the fish beneath, but the patterns on the surface reveal its presence. Gravity does the same with dark matter. Every time light bends too much, every time galaxies cling together more tightly than they should, gravity is whispering the same message. There's more here than meets the eye. Think of the universe as a great river system. The bright galaxies are the shining reflections on the surface, beautiful but only part of the story. Beneath that, shimmer flow vast, silent currents of invisible matter. You can't touch them or see them, but they guide everything that drifts above. For all its influence, dark matter behaves with perfect calm. It doesn't spark, collide, or glow. It passes through itself and through ordinary matter as if nothing were there. Physicists call it non-collisional, meaning it doesn't bump or interact in the usual ways. Ordinary matter, like the atoms in your body, constantly trades energy through light and electricity. Dark matter does not. It experiences gravity, and as far as we can tell, little else. If it did interact more strongly, if it scattered light or clumped under pressure, the universe would look completely different. Galaxies might shine with strange radiation, or form distorted shapes we could spot easily. But they don't. The night sky is still calm and dark, which means dark matter keeps to itself. That quiet independence is exactly why it could form the backbone of the cosmos. In the first moments after the Big Bang, the universe was hot and crowded. Ordinary matter couldn't settle down. Photons, the particles of light, kept bouncing off charged particles, stirring everything like boiling water. But dark matter ignored all that commotion. It felt only gravity, and gravity pulled it gently together into clumps. Those clumps became the seeds of structure, the first blueprints for galaxies. When the universe cooled enough for normal matter to calm down, it drifted into those invisible wells like dust settling into grooves. Dark matter didn't build galaxies directly. It shaped the landscape where they would grow. Without it, space might still be filled with nothing but glowing gas, bright but empty. Ironically, the weakest of all forces, gravity, became the architect of everything. On human scales, gravity seems feeble. A small magnet can lift a paperclip against the pull of an entire planet. Yet across billions of years and endless distances, gravity's patience wins. It sculpts galaxies, clusters, and vast cosmic patterns that endure. Sometimes, the universe reveals these patterns in spectacular ways. When two galaxy clusters collide, their clouds of gas crash together, heating up and shining in X-rays. But their dark matter halos glide right through each other, untouched. The visible material slows, but the invisible passes on, leaving gravity's fingerprints in the aftermath. It's a breathtaking sign that dark matter is real, a quiet separation of light and mass, proof written across the heavens. To astronomers, such events are like glimpses into the hidden current beneath the river. The galaxies drift, the light bends, but the invisible hand guiding them never changes. Everything we know about dark matter comes from watching how it moves the things we can see. It's like trying to understand the shape of a bird in tall grass by the way the stalks sway as it passes. Over decades, scientists have pieced together the creature's outline from those movements. Dark matter forms halos around galaxies, connecting them with unseen bridges and holding the cosmic structure in place. It doesn't break the laws of physics, it completes them. Without it, the math of gravity would predict chaos. Stars would fly apart, galaxies would never form, and clusters would dissolve into dust. But with it, everything holds together. It's as if an invisible hand steadies the spinning record of the cosmos. Light paints the universe, but gravity draws the outlines. Every spiral, every orbit, every curve we see is traced upon a framework of the unseen. Follow those lines far enough, and they connect into a delicate interlocking design, the cosmic web. When astronomers first mapped the universe in 3 dimensions, they expected a random sprinkle of galaxies scattered through space. What they found instead was astonishing, a vast network stretching across billions of light years. It looked less like chaos and more like an immense lacework, woven from invisible threads. This grand structure became known as the cosmic web. It's the skeleton of the universe, the scaffolding on which all light hangs. Galaxies and clusters mark its filaments like glowing beads on strings, while between them lie immense voids, regions so empty that hardly a single galaxy exists inside. To glimpse this web is to see the quiet architecture behind creation itself. At first, it seemed impossible. The early universe was almost smooth, a hot fog, with only tiny ripples in density differences so small they barely existed, about 1 part in 100,000. Yet those ripples were enough. Gravity, slow and tireless, began gathering matter into slightly denser regions. Over billions of years, those small knots grew into filaments and clusters. Dark matter was the patient builder behind it all. Ordinary matter was too busy glowing, colliding, and scattering in that early light. It couldn't form stable structures yet, but dark matter ignored the light completely. It started clumping early, forming the first invisible threads of the cosmic web. When the gas of normal matter finally cooled, it drifted into those filaments, where gravity drew it tighter and tighter, until the first stars began to shine. The result is a universe balanced between light and dark bright galaxies along filaments of unseen matter, surrounded by enormous, silent voids. Some filaments stretch for hundreds of millions of light years. If you could step outside the universe and look down, the pattern might resemble the branching of neurons in a brain or the roots of a tree glowing faintly against the dark. Astronomers use words borrowed from life itself to describe it: filaments, nodes, clusters, voids. The filaments are the cosmic highways. The nodes are intersections where clusters of galaxies gather. The voids are the quiet deserts between them. The universe is like a foam, the galaxies forming the thin walls, and the voids the vast bubbles inside. To study this immense structure, scientists map millions of galaxies using huge surveys of the sky. When they plot their positions in 3 dimensions, a breathtaking image appears, not random points, but an elegant web. Each filament hums with gravity's pull. Every void balances the tension. The most extraordinary part is that computer simulations can recreate this same pattern almost perfectly. Using a model called lambda-cold dark matter, scientists start with simple physics. The universe expands, gravity pulls, and dark matter moves slowly and interacts weakly. Out of those few ingredients, a digital universe takes shape. Tiny clumps of matter merge into larger ones, forming filaments and clusters that look almost identical to what telescopes see. It's one of the quiet triumphs of modern cosmology, that the universe's beauty emerges naturally from just gravity, time, and the unseen. In the model's name, the lambda stands for dark energy, the mysterious pressure causing the universe to expand faster and faster. Cold means the dark matter moves slowly enough to stick together, rather than zipping apart too quickly to form structure. Together, dark matter and dark energy make up about 95% of everything that exists. The stars, gas, and planets, the part we call the universe, make up only the remaining 5%. That realization is humbling. What we see is only the faint shimmer outlining a vast unseen design. The largest patterns in the cosmos aren't drawn by light, but by the absence of it. Every galaxy is a lantern hanging on the framework of the dark. The cosmic web is a masterpiece, drawn in reverse, its true lines defined by what can't be seen. There's a graceful balance in this structure. The filaments are narrow and dense, while the voids are vast and empty. The universe is mostly nothing, yet that nothing gives shape to everything. The emptiness allows the light to exist, just as silence gives music its rhythm. Without voids, the web could not breathe. Without the dark, the light could not shine. Even the way galaxies spin seems influenced by the web. Many align their axes along its invisible filaments, their motion shaped by the slow flow of matter through the network. It's as if the entire universe shares a quiet choreography, a gravitational rhythm set in motion billions of years ago. To picture it, think of frost on glass or the veins in a leaf. Each curve forms naturally, repeating simple physical rules again and again. Gravity does the same, turning chaos into harmony through patience and time. Even the voids have a strange peace. Some are so vast that if the Milky Way sat inside one, there might be no other galaxy within reach of sight. Yet they are not sad places. They are pauses in the cosmic composition. They give the web its balance, its breath. From a distance, the cosmic web seems timeless, but it is changing. Galaxies continue to fall along the filaments, merging and growing heavier. The voids expand as the universe stretches, gently pulling the filaments apart. Billions of years from now, the web will thin and fade, its bright threads stretched beyond view. For now, it remains a vision of quiet order. Galaxies sparkle along invisible bridges. Clusters shine like cities, connected by gravity's highways. It's the universe's greatest expression of balance. Order from chaos, harmony from darkness. When astronomers map this structure, they aren't just charting matter, they're reading the autobiography of the universe. Each filament, each void, tells the story of gravity's long, steady work. The same force that holds planets in orbit, keeps galaxies from flying apart, and bends light on its journey through space. Gravity is the pen, and the universe is its drawing, a web of light suspended on threads of dark. Built from silence, it still gleams, the hidden and the visible, forever intertwined. The shape of the universe is not an accident. It's written in the quiet patience of gravity, and traced in light that has traveled for billions of years to show us how the dark has shaped everything we know. Light moves in straight lines, or so it seems from where we stand. A sunbeam through a window lands cleanly on the floor. A flashlight cuts a neat path through mist. Our eyes trust straightness because here on Earth, space behaves well. But in the deep universe, space itself bends, and light is forced to follow. It twists, stretches, even loops back on itself. Not because it wants to, but because gravity reshapes the very fabric it travels through. That bending of light is one of the clearest fingerprints of dark matter. Astronomers call it gravitational lensing, a quiet but extraordinary effect predicted by Einstein's theory of general relativity. Imagine placing a glass bowl over a photograph of stars. The picture distorts. Some points of light stretch into arcs, others appear twice, and faint shapes brighten unexpectedly. In the universe, clusters of galaxies act like that invisible glass bowl, warping the light from even more distant galaxies that lie behind them. To astronomers, the cosmos becomes a hall of mirrors that follows the rules of physics. When the lens is massive, a great cluster of galaxies, or even a wall of dark matter, the bending is dramatic. The distant light can be stretched into long arcs or perfect circles called Einstein rings, named for the physicist who first described how gravity could bend light. By studying these distortions, scientists can map where the hidden mass lies. Every arc of light marks a path curved by gravity, and that curve points back to something unseen but real. Light cannot touch dark matter directly, yet it traces its shape like ink outlining invisible contours. Even when the bending is slight, what astronomers call weak lensing, it leaves measurable marks. The shapes of millions of faint galaxies appear stretched in the same direction by tiny amounts. Those small signals, added together, form a map of the dark. It's painstaking work. Telescopes must be precise enough to notice distortions smaller than 1%, and computers must separate cosmic effects from the blur of instruments and atmosphere. But the result is remarkable. An image not of light, but of gravity itself. One of the most dramatic examples comes from a pair of colliding galaxy clusters known as the Bullet Cluster. About 150 million years ago, two enormous swarms of galaxies slammed together in deep space. The gas clouds, ordinary matter, crashed and slowed down, heating up into bright X-ray knots. But the invisible mass, the dark matter, didn't stop. It passed straight through, unaffected by friction or pressure. When astronomers mapped the region with gravitational lensing, they found that the heaviest parts of the system were not where the visible gas glowed, but ahead of it. This separation between light and gravity was undeniable. If gravity came only from visible matter, the glowing gas should have matched the gravitational map, but it didn't. The lensing showed that most of the cluster's weight belonged to something that didn't collide or slow down something transparent and massive. The Bullet Cluster became one of the strongest proofs that dark matter is real. It was like watching two invisible ghosts glide through each other, while the visible debris lagged behind. Gravitational lensing isn't just a curiosity. It's one of the most powerful tools in cosmology. It allows astronomers to weigh galaxies and clusters like items on a cosmic scale. By comparing how light bends at different distances, scientists can even watch how structure in the universe has grown over time. Light that has been traveling for billions of years carries the record of its journey. Each distortion, each stretched image, tells part of the story of how matter gathered and evolved. These maps are now so detailed that they can distinguish between competing ideas about what dark matter might be. If dark matter moves slowly, as cold dark matter does, the lensing patterns line up neatly with the cosmic web we see in simulations. If it moved faster, as warm dark matter would, that structure would blur, smearing out the fine detail. By measuring how light bends, astronomers are narrowing down the properties of the invisible. And for all its complexity, lensing is deeply visual. Observatories publish images showing massive galaxy clusters surrounded by curved arcs of light background galaxies stretched and duplicated by gravity. Sometimes a single galaxy appears several times, arranged in circles or shimmering streaks. Nature has built its own telescope, using gravity as a lens far more powerful than anything humans can construct. There's a quiet irony in this. We use light to study what will not shine. Dark matter refuses to glow, yet light obeys its influence so faithfully that we can map the dark by its distortions. Wherever light strays from a straight path, we know that something heavy, unseen, has tugged it aside. The sky above us is filled with invisible lenses, warps in space-time created by massive clusters, halos, and filaments of dark matter. Every beam of light that reaches us carries a layered story of its passage through that distorted terrain. The night sky we see is not a perfect window, but a mosaic of gentle deceptions, a portrait painted through curved glass. Yet those curves are what make astronomy possible. Without them, we could never see the dark, never weigh the invisible. Each arc of light, each stretched shape, is a clue written in gravity's script. Space, it seems, is the only place where mirrors that twist reality make truth clearer. There's something deeply human about this kind of discovery. We rely on light to see, and yet we've learned to read meaning from its deviations, learning not from perfection, but from distortion. We've turned flaws into language. The arcs and rings scattered across space aren't imperfections, they're messages. Light, bent but honest, tells us what gravity has done. Follow those distortions far enough back in time, and you reach the faint afterglow of the universe's birth, the cosmic microwave background, or CMB. Even there, in the oldest light of all, the fingerprints of dark matter remain. Long before stars, before galaxies, even before atoms existed in their modern form, the universe was a dense, hot fog of particles and light tangled together. Photons, particles of light, couldn't travel freely. They bounced constantly off electrons and protons in a glowing soup. If you could have stood there, you wouldn't have seen darkness at all. You would have seen nothing, because light couldn't escape. The universe wasn't dark, it was blinding. Then it expanded and cooled. About 380,000 years after the Big Bang, the temperature dropped enough for electrons to combine with protons, forming neutral hydrogen atoms. The fog cleared. For the first time, light could travel unhindered, racing outward like ripples across an endless pond. That light is still traveling today. It has stretched and cooled as space itself has expanded, and now it reaches us as a faint, nearly uniform glow, the cosmic microwave background, the oldest light in existence. If you've ever seen the static between channels on an old television, a tiny fraction of that noise is the echo of this ancient radiation. It's everywhere, filling space, washing through the Earth, even passing through you right now. The CMB is the universe's memory of its first moment of clarity. To the eye, it seems perfectly smooth. But when astronomers studied it closely with satellites like COBE, WMAP, and Planck, they found tiny variations, differences in temperature only a few thousandths of a degree. Those faint freckles are the seeds of all cosmic structure. The slightly denser patches mark where gravity began to gather matter. The slightly lighter patches mark where it would thin into vast voids. Without dark matter, those tiny ripples would never have grown into galaxies. Ordinary matter was still caught up in radiation, tossed around by photons like dust in sunlight. Every time it tried to clump under gravity, light pressure blew it apart again. But dark matter didn't interact with light. It could begin forming gravitational wells even while the rest of the universe was still glowing and chaotic. Later, when the ordinary matter cooled, it fell into those wells, settling into the patterns dark matter had already drawn. In this way, dark matter gave structure its head start. The ripples in the CMB are more than temperature differences. They're the gravitational fingerprints of the unseen. Maps of the microwave background resemble a mottled sphere colored with reds and blues. Red for slightly warmer regions, blue for slightly cooler ones. It might look random, but that pattern encodes the precise ingredients of the universe. From it, scientists can calculate how much matter exists, how much of that matter is dark, and how much of the cosmos is driven by dark energy, the mysterious force accelerating its expansion. The numbers that emerge are astonishingly clear. About 5% of the universe is ordinary matter, the atoms that make up stars, planets, and life. About 27% is dark matter. The remaining 68% is dark energy. These figures aren't guesses. They come straight from the data, measured from the CMB's tiny ripples, like notes from an ancient chord. It's as though the universe left its own accounting book written in light. To picture it, imagine a perfectly calm pond at dawn. The first light touches the surface, and you see faint circles spreading outward, small reminders of where the water was disturbed. Each ripple carries memory. Scale that image up to the size of the universe, and you have the CMB. It's the cosmos, remembering its own beginning. Those ripples are precise. The spacing between their peaks and troughs reveals how sound waves move through the early plasma, which depends on the mix of matter and radiation present at the time. From that pattern, scientists infer the universe's composition and even its future. Listening to that ancient light is like hearing the echo of a bell and knowing its shape from the sound alone. And the light hasn't stopped arriving. Every second, photons that have been traveling for nearly 14 billion years reach Earth, carrying with them a record of the universe before the first star was born. They pass through the air, through the ground, through you. They are the background hum of existence, the steady whisper beneath all cosmic music. If the early universe had been perfectly uniform, nothing would exist today. Gravity would have had no foothold, no seed to build upon. Matter would have remained evenly spread, and no stars would have ever formed. The 1 in 100,000 irregularities in the CMB are what made everything possible. Those tiny imperfections became galaxies, stars, and eventually, life. Imperfection, it turns out, is the source of beauty. Each new measurement of the cosmic microwave background sharpens our picture of the past and deepens our understanding of dark matter's role in shaping everything. It was the silent partner, the unseen architect. The galaxies shining across the night sky are the bright outlines of the shapes it first traced. The cosmic microwave background is the universe's autobiography, written in radiation, telling of a dense, hot beginning, of cooling and expansion, of gravity's quiet work long before light could roam free. Its ripples echo through every atom, every star, and through us. When you look up at the night sky, you're seeing the latest chapter of that ancient story. The faint light around you began its journey when the universe took its first breath. It carries the memory of how darkness made room for light, and how from that balance, everything we know was born. By the time the universe reached a few 100 million years of age, the fog had lifted. The bright afterglow of the Big Bang had faded into the background, and darkness reclaimed the sky. Yet this was not an empty darkness. Beneath it, gravity was at work, sculpting an invisible landscape of structure. Dark matter had already begun to clump long before the first stars came alive, free from the drag of light, moving under its own quiet pull. It gathered into vast halos, huge, roughly spherical cocoons of unseen matter. Each one was a gravitational seed, a cradle waiting for galaxies to form. If you could have seen the cosmos, then you would have found a universe full of ghostly bubbles, invisible yet heavy, each humming faintly with the promise of creation. Inside those halos, ordinary matter, hydrogen and helium gas, began to fall, cooling as it collapsed. The gas swirled and condensed, drawn deeper into the gravity wells carved by dark matter. As the pressure grew, some regions became hot and dense enough to ignite. The first stars flickered to life, small and brilliant, burning in the dark like sparks catching in dry tinder. Dark matter didn't shine, but it guided everything that did. It shaped the stage, held the actors in place, and steadied the dance of creation. Without it, galaxies would have been slow to form, scattered, and faint. The sky would have been lonelier. The halos themselves formed in a kind of hierarchy. Small ones appeared first, merging again and again into larger systems. When two halos collided, their dark matter clouds passed through one another almost undisturbed, blending smoothly to form bigger, heavier homes for future galaxies. The gas, collisional and chaotic, was less polite. It crashed, heated, cooled, and ignited in bursts of new star formation. Over billions of years, that process built everything from tiny dwarfs to the majestic spirals and ellipticals we see today. Every galaxy we know, including our own Milky Way, rests at the center of such a halo. The glowing stars, planets, and dust we see are only a small fraction of the whole. The halo stretches hundreds of thousands of light years beyond the luminous disk, its invisible mass outweighing all the visible matter many times over. When astronomers simulate the universe on computers, they begin with only dark matter, particles, and gravity. Out of that simplicity, halos appear naturally, clustering and merging in graceful patterns. When gas physics is added, luminous galaxies form inside them, perfectly aligned with what telescopes observe. It's as though the universe is being built from the shadows outward, the dark matter setting the mold and light filling it in. There's a quiet beauty in that arrangement. For all our fascination with stars and glowing nebulae, the real architecture of the cosmos belongs to the unseen. Dark matter is the potter's hand that never shows itself, shaping the clay of the visible universe. Without its hidden support, even the elegant spirals of galaxies like the Milky Way would unwind. Their arms would drift apart, their stars scattering into the void. The dark matter halo gives structure its backbone and rhythm. Where halos grew quickly, galaxies became crowded and bright, using up their gas in wild bursts of star formation. In calmer regions, halos expanded more slowly, and star formation stretched gently across billions of years. The cosmic web, with its filaments and nodes, acted as the highway system that connected everything together. Gas flowed along those filaments like rivers, feeding galaxies that formed at their intersections. Each halo was a basin at the meeting of streams, gathering material and turning it into light. That flow made the universe both structured and alive, a grand, self-organizing network where gravity directed the rhythm of growth. Even now, dark matter continues to guide the shape and motion of galaxies. It determines how fast they spin, how massive they can become, and how they interact when they meet. When galaxies collide, it's their halos that touch first. The invisible clouds blend and merge long before the stars themselves come close. The spectacular fireworks of colliding galaxies that telescopes capture are only the surface of a much deeper event. Beneath that display, two immense halos are merging in silence, their gravity slowly knitting them together into a single, larger home. Astronomers see this influence even on smaller scales. Tiny dwarf galaxies orbiting giants like the Milky Way seem to be wrapped in dense knots of dark matter. Without those knots, their weak gravity couldn't hold them together against the tidal forces of their larger neighbors. Dark matter acts like cosmic glue, preserving delicate structures that would otherwise be torn apart. Without it, the universe would look utterly different. The early gas would have remained evenly spread, too warm and thin to form stars quickly. Galaxies, if they existed at all, would be rare and dim, faint smudges lost in an endless gray. The night sky, as we know it, rich with billions of shining islands, would never have appeared. The dark made the light possible. The first stars born within those halos likely lived brief and brilliant lives. They burned with fierce heat, sending floods of ultraviolet light into their surroundings, burning away the last traces of the cosmic fog. Their violent deaths scattered the first heavy elements, carbon, oxygen, iron, into space, seeding future generations of stars and planets. Those elements would later form the building blocks of everything, from the rocks beneath our feet to the air in our lungs. In that sense, the unseen architect didn't just build galaxies. It prepared the universe for life that would one day look back and wonder about its origins. Dark matter's quiet gravity gave the cosmos its shape, but it also set in motion the chain of events that made consciousness possible. Astronomers continue to refine their understanding of these halos, how they evolve, how galaxies move within them, and how they grow over billions of years. The physics can be intricate, yet the idea remains simple. Where dark matter gathers, light follows. The halos form the wells, and the galaxies are the reflections shimmering on their surfaces. Look at a photograph of the Andromeda Galaxy, its graceful arms winding through blackness. It's easy to forget that most of what holds it together cannot be seen. The visible disk spans perhaps 100,000 light-years, but its dark halo extends 10 times farther, silent and immense. The stars trace the outlines of a deeper structure, a sphere of gravity sculpted by invisible mass. That halo keeps the stars in orbit, prevents them from drifting away, and shapes the galaxy's rotation. Without it, the spiral would unravel. It's a structure made not of gas or dust, but of countless dark matter particles moving together like a ghostly swarm, each orbiting the others under the shared pull of gravity. They rarely collide. They simply coexist, forming a stable cloud that anchors everything we can see. This idea of halos grew naturally from the study of galaxy rotation. When Vera Rubin and others measured how quickly stars moved in the outer regions of galaxies, the data showed they were going far too fast. The simplest explanation was that each galaxy sat inside an enormous reservoir of unseen mass. Once that was included, the puzzle resolved itself. The galaxies stayed intact. Their motions suddenly made sense, and the universe fit together again. Halos don't only hold single galaxies, they also bind families. Small companions, like the faint dwarf galaxies orbiting the Milky Way, move within its dark halo, like sparks circling a campfire. Some are so dim they contain only a few thousand stars, yet they remain loyal to our galaxy because the halo's gravity reaches far beyond the visible disk. Inside that invisible bowl, stars and gas can move freely, but never escape. The gravitational well is deep, bending their paths into elegant, stable orbits. Even at hundreds of kilometers per second, the stars are caught, their motions woven into the coherent rhythm of the galaxy. When two galaxies merge, their halos overlap first, cushioning the encounter. Over long stretches of time, the dark clouds blend, forming a single, larger halo. Inside it, the luminous galaxies spiral toward one another, their stars slowly mixing into a new, brighter whole. Galactic mergers are often portrayed as violent collisions, but at their core, they are graceful two invisible halos performing a slow gravitational waltz. Dark matter doesn't rush. It doesn't burn or burst. It builds quietly, patiently, over cosmic time. It holds galaxies steady, keeps stars in orbit, and gives the universe the structure it needs to exist. The galaxies are its art, fragile yet enduring, light carved upon a foundation of shadow. If you could see the dark halos around galaxies, they would look like glass spheres surrounding lanterns, clear, heavy, and alive with motion. The stars glow only in the very center, while the halo stretches outward, silent and vast. It is not a shell, but the true body of the galaxy, a deep ocean in which the bright islands of stars float. Its mass outweighs them by a factor of 10 or more. Its gravity keeps them bound, turning chaos into order. Every galaxy, no matter how brilliant or distant, lives inside such an invisible cocoon. It is both cradle and anchor, the quiet foundation beneath the universe's luminous surface. The visible spirals and clusters we admire are just the tips of those hidden mountains of mass, glowing edges of a grander whole. The dark may not shine, but its touch is everywhere, pressing softly into the light of every star, shaping every orbit, holding every world in place. Not every halo is the same. Some are compact and dense, pressing their mass toward the center. Others are softer, more diffuse, with gravity spread gently throughout. Astronomers have spent decades trying to understand how dark matter arranges itself inside these halos, and the story is still unfolding. In computer simulations, halos tend to form with steep central peaks regions where the density rises sharply toward the middle. Scientists call these cusps. But when astronomers look at real galaxies, some seem to have smoother, flatter centers instead cores rather than cusps. This mismatch is known as the core cusp problem, and it's one of the most persistent puzzles in modern cosmology. Perhaps dark matter behaves a little differently than expected. Maybe it can nudge or scatter in ways the simplest models don't capture. Or perhaps the visible matter, the gas and stars inside galaxies, reshapes the halo over time. Explosions of supernovae, the violent winds of young stars, or the slow tug of rotating gas clouds could all disturb the inner dark matter. smoothing out what simulations predict to be sharp. Whatever the cause, halos remain remarkably resilient. They have endured collisions, mergers, and the steady stretching of cosmic expansion over billions of years as galaxies grew, collided, and changed. Their halos stayed in place, patient, steady, and strong. They are the silent scaffolds of cosmic history. To grasp the scale, imagine the Milky Way suspended in its invisible halo. The bright disk we see from Earth, those hundreds of billions of stars tracing a glowing band across the night, spans roughly 100,000 light-years. But the halo around it extends more than 10 times farther. It is so vast that our neighboring galaxy, Andromeda, is already brushing its edge. The two halos are slowly mingling, their outermost layers blending long before the galaxies themselves will merge. In about 4 billion years, when the Milky Way and Andromeda finally come together, their halos will have been intertwined for nearly all of cosmic history. The dance of their invisible outskirts has already begun. The Milky Way's halo is not empty, though we cannot see it. It's threaded with streams of stars, long, delicate trails, marking the paths of smaller galaxies and clusters that have been pulled apart by gravity. Each stream is a scar, the lingering memory of a companion torn to pieces. By tracing their shapes and motions, astronomers can infer how dark matter is distributed through the halo. Like archaeologists rebuilding a temple from scattered stones, they use these faint traces of light to map what cannot be seen. The halo does more than just hold the galaxy together. It also controls how the Milky Way evolves. Gas falling into the halo heats up as it descends, forming a warm envelope that can later cool and flow inward to form new stars. The balance between that inflow and the outflow from stellar winds and supernovae determines a galaxy's future, whether it remains bright and active or fades into quiet dormancy. In this sense, the halo acts like a cosmic thermostat, setting the temperature and tempo of galactic life. For something invisible, halos are astonishingly influential. They decide which galaxies thrive and which fade away. They shape the speed of stars, the brightness of spiral arms, and the length of a galaxy's lifetime. Without halos, galaxies would be fragile, dissolving into space within a few billion years. With them, they can survive and spin calmly for ages, their light held steady within a cradle of darkness. It's a serene image, a lantern, glowing softly inside a glass sphere, protected from the chaos around it. The light and the dark are not enemies, but partners, bound together by gravity's quiet logic. Across the universe, this pattern repeats endlessly. Every spiral, every elliptical, every faint cluster of stars lies within its own invisible shell. Even in the emptiest stretches of space, where galaxies are few, each one still rests inside its private sphere of gravity. When you gaze at the Milky Way on a clear night, you're seeing only its luminous core. Beyond those stars stretches a vast, unseen halo, ancient, silent, and patient. We drift inside it, bound to it as surely as the stars themselves. Our galaxy's halo doesn't shimmer, but its presence defines the structure of the sky. It is gravity's quiet masterpiece, immense yet delicate, powerful yet invisible. A structure both infinite and intimate, holding the lantern of light within a sphere of darkness. The Milky Way, from our perspective, appears as a graceful spiral of stars sweeping across the heavens. But what we see is only a thin surface. The true body of our galaxy is far larger. It is wrapped in a massive halo of dark matter. stretching hundreds of thousands of light years in every direction. We live deep inside that invisible realm, surrounded completely by it. Every atom, every beam of starlight, every drifting comet moves through this unseen ocean. The particles of dark matter pass through us constantly, billions of them each second, yet we feel nothing. There is no wind, no resistance, not even a whisper. Still, its gravity shapes everything. The orbit of the sun, the paths of planets, the movement of distant stars. The halo is the invisible stage on which the Milky Way performs its slow, elegant dance. The sun itself races around the galactic center at about 220 kilometers per second, completing a single orbit every 230 million years. As it travels, it carries the solar system through the dark matter halo, like a ship sailing across a calm sea. The dark matter doesn't push or drag. It simply defines the ocean's contours, the unseen currents that shape our journey. If you could somehow make the halo visible, you would see a faint, ghostly sphere stretching far beyond the galaxy's bright spiral arms. The visible Milky Way would appear as a small candle floating inside a glass globe hundreds of thousands of light years wide. For astronomers, studying this halo is like charting the depths of a dark ocean by watching the drift of boats on its surface. The motions of stars reveal the gravity beneath, just as the sway of seaweed reveals the pull of unseen tides. Among the most beautiful traces of the halo are stellar streams, long ribbons of stars winding across the sky. These streams form when smaller galaxies or clusters venture too close to the Milky Way and are slowly pulled apart. Their stars spill out, following their orbits in luminous trails that can wrap around the galaxy. Each one maps the curve of the dark halo, showing where gravity tugs and how the invisible mass is arranged. The Sagittarius stream is perhaps the most famous of these. It is the remains of a small galaxy being absorbed by our own, its stars stretched into a looping ribbon that circles us like a ghostly band. These delicate trails tell a story of ongoing creation, the Milky Way growing by merging with its smaller neighbors, its halo recording every encounter like ripples in still water. From studies of these streams, astronomers know that the Milky Way's halo is not perfectly smooth. It has knots, ridges, and waves, evidence of ancient mergers and gravitational disturbances. Even the dark is alive with motion, constantly shifting as the galaxy evolves. Each passing satellite galaxy leaves a mark, a subtle ripple in the invisible mass that can persist for billions of years. Though we float within this vast sea, dark matter does not touch us in the way ordinary matter does. Its particles pass through Earth, through mountains, through our own bodies without ever colliding. The thought may sound eerie, but it's strangely peaceful. We are immersed in the dark, carried effortlessly along in its quiet current. The halo's gravity anchors the Milky Way. It keeps stars near the edge moving securely in their orbits, preventing them from drifting away into intergalactic space. Without it, the galaxy's outer arms would unravel, fading like smoke on the wind. The halo is the galaxy's frame and foundation, the unseen balance behind the visible. Astronomers still debate its exact shape. Some evidence suggests it's slightly flattened, like a sphere pressed gently at the poles. Others hint it may be lopsided, stretched by ancient collisions or by the influence of the nearby Andromeda galaxy. Whatever its geometry, the halo defines the true size of the Milky Way, a size far beyond what the eye can see. It also acts as a net, capturing smaller galaxies that stray too close. The Milky Way's faint satellite galaxies, tiny smudges of light, with only a few million stars, are held in place by its vast gravity. Some will eventually spiral inward, merging with the Milky Way and thickening its halo even more. The galaxy we inhabit is still assembling, still changing, shaped by the slow, steady hand of the dark. Every orbit, from the sun's grand circuit to the dance of stars within clusters, is guided by this invisible force. Space is not empty. It's filled with substance that neither glows nor resists. We are adrift in a gravitational ocean that gives form to everything we see. When you look up at the Milky Way's band of light, remember that it is only the bright skin of a much greater structure. We are not outside observers. We are part of it, moving quietly within its vastness. The halo doesn't stop at the edge of the stars, it surrounds us completely. Dark matter gives our galaxy its strength, its endurance, and its grace. It is why the Milky Way has held together through eons of turbulence. We are passengers aboard a ship of light and shadow, sailing through a sea we cannot see. Its waters are still, but their presence is written in every orbit, every shimmer of starlight, every moment of balance in the night sky. By now, the case for dark matter seems nearly airtight. Galaxies spin faster than visible mass allows. Light bends more sharply than ordinary gravity can explain. Clusters of galaxies stay bound together, even when their visible matter is far too little to account for the pull. Everywhere astronomers look, the universe behaves as if something invisible is at work. Yet before leaping to new physics, scientists had to ask a humbler question. What if this dark matter wasn't strange at all? What if it was something ordinary, something we had simply failed to notice? It was a reasonable place to begin. Space is vast, and the cosmos hides faint things well. Perhaps the missing mass was made of dim stars that had slipped beneath the limits of our telescopes. Maybe the universe was full of unlit suns, small, cold, and quiet. For a time, this idea was compelling. Astronomers imagined swarms of brown dwarfs, stars that never quite ignited, or ancient white dwarfs, the burned-out cores of long-dead suns. Some even proposed wandering worlds, rogue planets drifting between the stars without a home. Collectively, these faint bodies earned a name: MACOs, short for Massive Compact Halo Objects. The acronym was catchy, and for a while, it offered a hopeful explanation. Maybe galaxies were simply crowded with invisible cold stars, orbiting unseen in their halos. But as telescopes improved, the evidence faded. When astronomers surveyed the skies with deep infrared cameras, they found too few of these dim stars to explain the missing mass. Even when they searched indirectly, watching for the subtle flicker of starlight as one of these objects passed in front of a distant background star, an event called microlensing the numbers didn't add up. MACOs exist, but not in the quantities required. You could scatter billions of failed stars through a galaxy and still come nowhere near the tenfold increase in mass needed to hold it together. Another suspect was hydrogen gas, the most abundant element in the universe. Cold hydrogen doesn't shine, and vast clouds of it could, in theory, lurk undetected in galactic halos. If galaxies were wrapped in such invisible blankets of gas, that could explain their extra weight. But when astronomers looked, they found no such fog. Cold hydrogen isn't completely dark. It glows faintly in radio wavelengths when hit by cosmic rays or starlight. Sensitive radio telescopes can pick up that emission, and the result was clear. There wasn't enough. Perhaps, some thought, the culprit was dust. Space is full of it, tiny grains of carbon and silicate that block light. Could the universe simply be dustier than we imagined? A comforting thought, but it didn't survive scrutiny either. Dust absorbs visible light, yes, but it re-emits it as infrared radiation. If enough dust filled the universe to mimic dark matter, the sky would glow gently in the infrared. It doesn't. Observations show only the faint whisper of dust, nowhere near the brightness such a theory predicts. Faint stars, cold gas, and cosmic dust, each a reasonable idea, and each eliminated in turn. The universe, it seemed, was hiding something more elusive. That left one more familiar suspect: black holes. They are the perfect candidates. On paper, invisible, massive, and known to exist in abundance. What if dark matter was simply a vast population of tiny black holes sprinkled through space? The idea was tempting, but once again, observations got in the way. If our galaxy's halo were filled mostly with black holes, their gravity would occasionally betray them. Each time one passed in front of a distant star, it would magnify the starlight through microlensing, creating a brief flare. Astronomers have spent decades monitoring millions of stars for such events. They've found a few, but far too few. The dark matter halo cannot be made of black holes in the usual range of sizes. Even if larger black holes, those with masses like the Sun's or greater, were common, we'd know it. Their mergers would produce a constant background hum of gravitational waves, a signal that instruments like LIGO and Virgo would easily detect. The silence of those detectors tells us that dark matter cannot be made mostly of such objects. Still, some black holes might play a smaller role. There's a possibility of primordial black holes, ancient relics from the first moments after the Big Bang. In that early chaos, dense knots of matter could have collapsed under their own gravity, forming black holes before the first stars existed. These primordial remnants might account for a fraction of dark matter, but not all. The math doesn't allow it. One by one, every ordinary explanation fell away. The stars, gas, dust, and compact remnants all could contribute a little, but not enough. It was as if astronomers had turned on every possible light and still couldn't brighten the room. The missing mass remained missing. This process of elimination was both frustrating and exhilarating. Frustrating because each promising idea failed under scrutiny. Exhilarating because the failures meant something truly new must exist, something beyond the realm of normal matter. The darkness wasn't an illusion or a calculation error. It was a clue. It pointed to a hidden form of matter, unknown yet fundamental. Scientists began to realize that dark matter must be fundamentally different from everything we know. It doesn't interact with light. It doesn't clump into stars or planets. It doesn't collide or slow down like ordinary gas. It feels gravity and, as far as we can tell, little else. That conclusion, while simple to say, marks a profound shift in our understanding of the universe. Reality, it seems, rests on two foundations: the visible and the invisible, the luminous world of atoms we know, and a silent shadow world that shapes it. Without dark matter, galaxies wouldn't exist, stars wouldn't orbit, and the universe might have remained a thin, featureless fog. The question now was no longer where dark matter was. It was what it was. What kind of particle could be so ghostly, so indifferent to light, and yet so essential? This question opened a new frontier, one that would unite astronomers, particle physicists, and cosmologists in the same pursuit. The search spread from observatories under the stars to laboratories deep beneath mountains and to massive particle accelerators probing the fabric of matter itself. If ordinary matter couldn't explain the universe's mass, then the answer had to lie in a new kind of particle, a relic of creation that still lingers everywhere. To qualify as dark matter, any such particle must meet strict criteria. It must be cold, meaning it moves slowly enough for gravity to gather it into galaxies. It must be stable, lasting for billions of years without decaying. And it must be weakly interacting, feeling gravity, but not light or the forces that govern normal atoms. One early clue came from a familiar source: neutrinos. These are real particles that stream through the universe by the trillions. They barely interact with anything, passing through planets as if they weren't there. In many ways, they behave like dark matter should: light, fast, and elusive. But there's a catch. Neutrinos move too quickly and carry too little mass. They can't clump under gravity to form galaxies the way dark matter must. The universe needs something heavier, slower, but just as invisible. The first major candidate was the WIMP short for weakly interacting massive particle. The name captures its essence: heavy enough to feel gravity, shy enough to ignore light. WIMPs could have formed in the hot early universe, when particles collided with enormous energy. As space expanded and cooled, most would have annihilated with each other, but a small number could have survived the leftovers from that primordial storm, drifting unseen ever since. WIMPs fit neatly into extensions of known physics, especially supersymmetry, a theory proposing that every known particle has a heavier partner. In that framework, the lightest supersymmetric particle would be stable, weakly interacting, and exactly what dark matter needs to be. This elegant overlap made WIMPs the favorite for decades. If WIMPs exist, they should occasionally collide with atoms, though very rarely. Such a collision would produce no flash, no burst of radiation, just the faint recoil of a single nucleus. Detecting that whisper would confirm dark matter's identity. This idea sparked decades of experiments. Detectors buried under mountains, tanks of liquid xenon kept at near absolute zero, shielded from cosmic rays and background noise. Each one waited for the softest tap in the dark. So far, they've found nothing conclusive, but even silence is data. Each non-detection helps narrow the possibilities, refining the search. Meanwhile, another candidate emerged from a completely different corner of physics: the axion. Unlike the WIMP, the axion wasn't born to explain dark matter at all. It was proposed in the 1970 seconds to fix a subtle flaw in quantum theory, a missing symmetry inside the strong nuclear force. The math demanded balance, and the axion was introduced to restore it. Then came a surprise. The same particle, if it existed, would behave exactly like dark matter. Axions would be extremely light, perhaps 1 trillion times lighter than an electron, but unimaginably numerous. Together, their collective gravity could account for the universe's missing mass. They would form a smooth, invisible mist, filling all of space. Axions are fascinating because they come from what's called a field, a continuous background energy that fills the universe. When that field vibrates, it behaves as if it's made of particles. You can think of it like the string of a violin. The string itself is continuous, but the sound it produces arrives in discrete notes. The axion field works in a similar way, its ripples acting like countless ghostly particles moving through everything without friction. If axions are real, they might occasionally transform into photons, particles of light, when passing through magnetic fields. Experiments have been designed to catch that process in the act, using ultra-strong magnets and exquisitely sensitive detectors. So far, The results are silent, but the search continues, ever more precise, listening for the faintest hint of the dark turning into light. Then there is the sterile neutrino, an even stranger possibility. Ordinary neutrinos already defy intuition, but some theories predict a hidden cousin, one that doesn't interact through any known forces except gravity. Such sterile neutrinos could have formed alongside regular neutrinos in the early universe, influencing how structure grew. Depending on their mass, they might count as warm, dark matter, not too fast to erase structure, but not as cold and clumpy as WIMPs. Observations of galaxy clustering and faint X-ray signals have set limits on their properties, but they remain a viable mystery. Each of these candidates paints a different picture of the invisible cosmos. WIMPs would be like scattered boulders, rare but heavy. Axions would be a delicate fog, light and pervasive. Sterile neutrinos would sit somewhere between the two, subtle and whispering. The truth could involve more than one of them, woven together into a complex, unseen web. What unites them all are the same three traits. They are cold, so gravity can gather them; stable, so they last as long as the universe; and shy, so they remain invisible to our instruments. That combination of qualities is rare, but not impossible, and it gives scientists hope that they are closing in on the truth. There's a strange kind of grace in the thought that the universe might be filled with ghostly marbles, endlessly rolling through matter without leaving a mark. They pass through us by the trillions, brushing against atoms without sound, moving as easily through mountains as through the air. These hypothetical dark matter particles are like perfect guests, quiet, polite, never disturbing the furniture, yet somehow holding the entire house together. Each experiment designed to find them brings a little more clarity, a small refinement to our picture of what might be out there in the dark. Whether the answer lies in heavy WIMPs, feathery axions, or some new form of matter no one has yet imagined, the search itself has reshaped our understanding of what the universe can be. It has shown us that the most important ingredients of existence might be the ones we cannot see at all. Somewhere in that cosmic shadow, the truth waits patient, silent, but inevitable. If these invisible particles are truly everywhere, the question becomes, how do we catch them? If dark matter is made of particles, they should already be flowing through us. Every second, countless numbers move through your body, through the ground beneath your feet, and deep into the planet itself. They don't glow, they don't slow down, they don't collide. But perhaps, on the rarest of occasions, one might nudge an atom ever so slightly, a whisper in the stillness of space. Detecting that whisper is one of the greatest challenges in science. The search for dark matter doesn't happen in the grand observatories that watch the stars. It takes place in quieter places, deep underground, beneath mountains, inside old mines, or under thick sheets of ice. These locations shield experiments from the constant bombardment of cosmic rays that could drown out the faint signal of a passing dark matter particle. Hidden in these underground cathedrals of science, enormous detectors sit in patient silence, waiting for a single, perfect tap from the invisible. The principle behind these experiments is simple, even if the execution is not. When a dark matter particle collides with an atomic nucleus inside a detector, it should cause that nucleus to recoil slightly. That motion might release a flash of light, a faint pulse of heat, or a minuscule vibration signals that can, in theory, be measured. But detecting such an event is like trying to hear a single snowflake land during a thunderstorm. The noise from ordinary particles, radiation, and even the natural radioactivity of the surrounding rock must be silenced as completely as possible. The detectors are extraordinary feats of precision. Some are vast tanks filled with liquid xenon, chosen because it is so pure that even a single collision can make it flash with ultraviolet light. Others use crystal detectors, cooled to nearly absolute zero, so that even the smallest jolt can be detected as a change in temperature, a vibration so faint it could be caused by an energy release smaller than a millionth of a degree. Every flicker, every pulse is recorded and analyzed. Most are discarded as background noise, but scientists look for the one event that doesn't fit. To give a sense of scale, one detector may operate for years without recording a single definitive dark matter event. The patience required is staggering. Researchers must separate real signals from a constant drizzle of false ones. Tiny flashes caused by cosmic rays, natural radiation, or even the slow decay of trace elements in the walls. Each experiment is a long meditation on the meaning of quiet. One of the leading projects, called Lux Zeppelin, rests nearly a mile underground in a former gold mine in South Dakota. Inside, several tons of liquid xenon sit, cooled and still. When a particle passes through and collides with a xenon atom, the impact produces a flash of ultraviolet light, detected by sensors that line the tank. It's like a giant ear pressed to the dark, waiting for the faintest sound. Other experiments take different paths. The super cryogenic dark matter search in Canada uses ultra-cold germanium and silicon crystals to detect tiny vibrations from a collision. These crystals are so sensitive that they can register energy changes smaller than what a snowflake makes when it touches the ground. Every atom, every tremor, becomes part of the universe's quiet conversation with itself. Around the world, these laboratories form a network of silence. In Italy, the Gran Sasso National Laboratory lies beneath nearly a mile of rock. In Japan, the Kamioka Observatory hums softly in an abandoned mine. Even the South Pole joins in, where the Ice Cube Neutrino Observatory listens to the faint flashes of light deep within Antarctic ice. Though its focus is different, it shares the same spirit, a willingness to listen to the universe rather than demand that it speak. Each year that passes without a detection teaches scientists something new. The silence narrows the field, ruling out possibilities and refining the range of masses and interactions dark matter could have. Every null result is a clue. Science moves forward not only through discovery, but through elimination. And dark matter has been generous with its quiet lessons. Still, the silence is not discouraging. For many physicists, it's part of the beauty of the search. The detectors are not monuments to disappointment, but to perseverance. The idea that one day, in the middle of an ordinary night, a single particle might finally leave a trace, a tiny flash, a soft vibration, is enough to keep the vigil alive. There have been moments of excitement, small blips, signals that seemed promising, whispers that might have been real. Each time, further studies showed that they were not. Yet each false alarm brings progress. Science, at its best, is patient. The thrill of discovery is matched by the discipline to wait for truth. And, in the case of dark matter, patience is the only currency that counts. The scientists who tend to these detectors often work alone, surrounded by stone and humming machinery, their instruments glowing softly in the dark. They calibrate, clean, and check readings in the silence of underground halls. Theirs is a slow, contemplative pursuit, a faith that the universe will eventually speak, even if it whispers. The search for dark matter has become a kind of global meditation, a network of quiet rooms, each holding its breath, each listening for the same faint note. Every so often, a flicker appears, a small pulse, a trace of light. For a moment, the room stops. Could that be it? Was that the touch of the invisible? Almost always, it isn't. But one day, it might be. And when that moment comes, when a signal is confirmed, it will mark one of the greatest discoveries in human history. Proof that we have directly detected a substance that has shaped the cosmos since its beginning. If that day comes, it will mean that humanity has finally heard the universe whisper back. Until then, the detectors keep their vigil, the lights stay dim, the world above carries on, unaware of the patient watch kept beneath its surface. The scientists remain, waiting for the faintest tap in the night. But what if the answer doesn't come from the ground at all? If dark matter refuses to reveal itself in the silence of our detectors, perhaps it leaves traces elsewhere, out there in the sky. The universe, after all, has been running its own experiments for billions of years. Galaxies collide, particles interact, clouds of dark matter overlap, merge, and stir. Somewhere among those cosmic events, faint signals may linger. This method is called indirect detection. Instead of catching a dark matter particle directly, scientists look for its potential byproducts, high-energy gamma rays, positrons, or neutrinos that could emerge when dark matter particles collide and annihilate each other. It's like searching for footprints rather than the creature itself. If two invisible particles meet and transform into visible energy, that burst of radiation might be the clue we've been waiting for. The best places to search are where dark matter is expected to be densest, such as the center of our galaxy. The Milky Way's core, swirling around its supermassive black hole, is packed with matter and energy, and likely a vast concentration of dark matter as well. If dark matter particles annihilate there, the region should give off a faint glow of gamma rays, the most energetic form of light. And indeed, instruments like NASA's Fermi Gamma Ray Space Telescope have seen something intriguing, an excess of gamma rays from the galactic center that doesn't match known sources. For a while, the data looked exactly like what WIMP annihilation would produce. The excitement was electric. Had we finally glimpsed the glow of the invisible? As it turned out, the signal was real, but the explanation wasn't simple. The galactic center is a noisy place. Pulsars, cosmic rays, and swirling gas clouds all produce gamma rays of their own. Some teams argued that the excess matched dark matter's signature perfectly. Others showed that a population of faint, fast-spinning neutron stars could explain it just as well. The fireflies were there, but were they real or only reflections on the glass? Beyond our galaxy, scientists turn their gaze to dwarf spheroidal galaxies, tiny, faint companions of the Milky Way, almost entirely made of dark matter. They are quiet, simple systems with little interference from other sources, making them perfect laboratories for the search. Dozens of telescopes have focused on them, hunting for faint gamma-ray glows. The results have been tantalizingly close, but not decisive. Small upticks, subtle signals, but never the firm, undeniable yes. Other instruments have looked for different byproducts. Some track positrons, the antimatter twins of electrons, which could emerge from dark matter annihilations. Detectors aboard the International Space Station have recorded mysterious surpluses of these particles. But the cosmos is full of noisy creators, pulsars, supernova remnants, and cosmic rays can all mimic the same pattern. Sorting out which signal belongs to dark matter is like trying to pick out one violin from an orchestra of thunder. High-energy neutrinos offer another clue. If dark matter collects in dense places like the sun's core, it might occasionally annihilate there, producing neutrinos that stream outward. The Ice Cube Observatory in Antarctica is listening for those ghosts, its detectors embedded deep in the ice flash with light whenever a neutrino passes through. So far, even that deep, cold watch has found nothing conclusive. The challenge is the same everywhere. The sky is loud. Cosmic rays bombard planets. Black holes roar, and stars explode. Dark matter, by contrast, whispers. Even if it leaves a trace, it must be teased from 1,000 brighter signals. Scientists model, compare, and reanalyze the data, refining their understanding bit by bit. And still, the chase continues. New observatories, like the Cherenkov Telescope Array, are being built with unprecedented sensitivity. They will map the heavens in exquisite detail, searching for the faint, diffuse glow of dark matter annihilation stretched across galaxies. Perhaps within that soft glow, the universe will finally reveal what it's been hiding. There is something profoundly poetic in this stage of the search. The idea that the key to the invisible might come not from silence underground, but from a flicker of light across the stars. We are, in a very real sense, hunting for shadows made of light traces that exist only in the brief moment when the invisible becomes visible. It's a dance between opposites, where darkness might finally reveal itself through the faintest flash. The idea is delicate and humbling. Even when no such light is found, the absence itself becomes a clue. Every non-detection sharpens the edges of what we know, drawing a clearer outline of what remains unknown. The silence isn't failure, it's the sound of progress marking its boundary. The faint horizon we keep pushing forward. If the whispers of dark matter can't yet be heard underground, and the sky offers only murmurs too ambiguous to trust, there remains one final stage for the search, a place where matter itself is torn apart and rebuilt, where we might coax the universe to repeat its own first moments. If the cosmos won't volunteer its secrets, we can try to make them ourselves. Astronomers watch the heavens, but physicists build them in miniature. Instead of waiting for dark matter to drift into their detectors, they recreate the energy of creation to see what might appear. This is the principle behind particle colliders. Smash familiar particles together with enormous energy and look for what goes missing. The most ambitious of these machines, the Large Hadron Collider near Geneva, is a 27-kilometer underground ring looping beneath the French-Swiss border. Inside it, protons are accelerated to nearly the speed of light before being steered into head-on collisions that mimic the conditions just after the Big Bang. Each collision is a small echo of the universe's birth. In that instant, temperatures and densities soar, and entirely new particles can appear. Particles not seen since the universe was seconds old. Surrounding the impact points are vast detectors, intricate layers of sensors that capture the debris spraying out from the collision. Most of what emerges is familiar: electrons, muons, photons, and the known fragments of atomic matter. But every now and then, the math doesn't balance. The total energy measured after the crash doesn't match what went in. Some of it has vanished, slipped quietly into the dark. This missing energy is one of the most important clues in the search for the unseen. Energy in physics is like money in a ledger. It must always add up. If something goes missing, it means that part of the energy has gone into creating a particle that isn't being recorded. If that invisible particle interacts too weakly to be seen, it could be a piece of the dark matter puzzle. The ATLAS and CMS detectors at the LHC are designed to spot these subtle imbalances, scanning billions of collisions per second, then filtering through the data for those rare patterns where energy disappears without a trace. In this way, physicists are not directly seeing dark matter, but its shadow, the shape left in the sum of everything else. It's a mirror image of what astronomers do. While telescopes map the gravitational influence of dark matter across galaxies, colliders attempt to produce the particles themselves, to understand what they are made of. Two ends of the same investigation, one following the footprints, the other trying to make the creature appear. The idea of creating dark matter may sound impossible, but it fits neatly into the story of the early universe. In the first seconds after the Big Bang, particles were constantly forming, colliding, and annihilating. If dark matter was born then, it should still be possible to recreate it under the right conditions. The challenge is knowing which ingredients to mix and how much energy to add to coax it into existence again. There's no menu. Instead, physicists test every possible combination, searching for a pattern, a bump in the data, or a missing spark that reveals something new. The subatomic world, however, is noisy. Collisions at these energies produce a storm of particles, a blur of tracks and flashes that fill the detectors. Most oddities turn out to be statistical flukes, brief coincidences that fade with more data. Physicists often joke that when you can't find your keys, you make new keys and see what fits the lock. In their case, those keys are new theoretical particles, supersymmetric partners, hidden photons, or even stranger creations that might unlock the mystery of the dark universe. So far, none have opened the door. The LHC has produced extraordinary discoveries, including the confirmation of the Higgs boson in 2012, a cornerstone of modern physics, but dark matter remains elusive. Yet even the Higgs may be part of the mystery. If dark matter interacts, however weakly, with ordinary matter, the Higgs field might be the bridge between the two, a subtle handshake between the visible and invisible universes. Physicists have been watching for the faintest changes in how the Higgs behaves, tiny deviations that could point to new particles hiding just beyond our reach. The LHC has not yet found that handshake, but its work is far from done. Every run narrows the possibilities, ruling out certain masses and interaction strengths, shrinking the shadowed territory where dark matter could hide. The process is meticulous and relentless. Searching a forest at night with a flashlight doesn't only reveal what is there, it shows you where not to look next. And sometimes, while searching for one thing, you find treasures you didn't expect. The collider has already deepened our understanding of how matter holds together, how energy condenses into particles, and how symmetry shapes the laws of nature. The pursuit of dark matter has become a compass for physics itself, pointing toward deeper truths even when the main goal stays out of reach. There's something poetic in using moments of immense violence, particles smashing together at near light speed to uncover something so calm and enduring as dark matter. Every collision is a miniature universe, expanding and cooling in a fraction of a second, perhaps producing a handful of invisible particles that slip away into silence. Detecting those absences requires near-perfect precision. The LHC's detectors are built like vast mechanical onions, each layer recording a different aspect of the collision light, charge, magnetic trails. When a particle vanishes, The instruments measure every remaining fragment so precisely that the missing energy stands out like a missing note in a symphony. The silence itself becomes data. Even if the LHC doesn't catch dark matter directly, it lays the foundation for what comes next. Plans for future colliders are already underway. Machines larger, more powerful, and more sensitive than anything we've built before. They will push deeper into the unknown, perhaps far enough to glimpse what lies just beyond today's horizon. Science doesn't continue from frustration, but from curiosity. Questions that resist easy answers are the ones that lead us forward, and dark matter remains one of the most beautiful of those questions. Whether the key lies hidden among the stars, buried deep underground, or flickering to life for an instant inside a particle accelerator, every approach brings us closer to understanding how the visible and invisible universes connect. Even without the final answer, the act of searching has transformed our picture of the cosmos. Discovery, in the end, is not only about what we find, it's about realizing how much remains to be found. As the hunt continues, another idea has been slowly stirring at the edges of physics. What if dark matter doesn't exist at all? What if, instead, we've misunderstood something more fundamental: gravity itself? Maybe there is no missing mass, only a missing piece in our equations. Perhaps the universe behaves differently on large scales than our current laws predict. This radical idea took shape in the early 1980 seconds. In the wake of Vera Rubin's groundbreaking measurements of galaxy rotation, physicist Mordechai Milgrom proposed a daring alternative known as modified Newtonian dynamics, or MOND. Newton's laws had stood unchallenged for centuries, perfectly describing motion within the solar system. But Milgrom suggested that at the tiny accelerations found on the outskirts of galaxies, gravity might not weaken exactly as Newton described. Instead, it might taper off more slowly, giving distant stars an extra gravitational boost that keeps them from drifting away. The elegance of MOND lay in its simplicity. With one small adjustment, the need for dark matter vanished. The theory could reproduce many of the same galactic rotation curves that had inspired the dark matter hypothesis in the first place. In some cases, it worked astonishingly well. It even captured subtle relationships, like the Tully-Fisher relation, which connects a galaxy's visible mass with its rotation speed, a pattern that dark matter models only approximate. To many, MOND seemed to have found a direct path through the puzzle. But the universe is rarely content with easy solutions. When MOND was tested on larger scales, such as galaxy clusters, cracks began to appear. The extra pull required to keep clusters bound together was far greater than MOND could explain. Ironically, even modified gravity needed a touch of invisible matter to make the math work. The theory also faltered when compared with the cosmic microwave background, the afterglow of the Big Bang. The delicate ripples in that ancient light encode how matter and gravity interacted in the early universe, and they match the predictions of the dark matter model almost perfectly, something MOND struggles to replicate. Still, MOND changed the conversation. It reminded physicists that no law of nature is beyond question. If Newton's equations might need adjusting, perhaps even Einstein's general relativity to our most complete description of gravity could be refined. That idea gave rise to a broader family of theories known collectively as modified gravity, or MOG. These models introduce new fields or forces that subtly alter how gravity behaves over cosmic distances or in extremely weak conditions. Some even attempt to unite dark matter and dark energy as two sides of the same underlying phenomenon. Modified gravity can mimic the effects of dark matter in striking ways. It reproduces galaxy rotation curves and sometimes even lensing patterns, bending light as if invisible mass were present. The appeal is clear. Why invent an entire class of particles if a few changes to our equations could explain the same effects? But as simulations grew more detailed, the balance of evidence tipped. Dark matter models naturally recreate the web-like structure of the cosmos, the vast filaments and voids seen in surveys, while modified gravity theories often stumble. They can handle galaxies, but they struggle with galaxy clusters, large-scale lensing, and the fingerprints left in the early universe's light. It's like navigating with two maps. One, the dark matter map, shows every mountain and river in clear detail. The other, modified gravity, outlines the roads but misses key bridges and coastlines. Both can get you across town, but only one consistently matches the terrain in every direction. Still, the alternative theories persist, not as mistakes, but as necessary provocations. They keep the scientific mind honest. History reminds us that even the most trusted ideas can turn out incomplete. Theories like Monde serve as a philosophical counterweight to certainty, a quiet voice asking, what if gravity itself has more to say? Some researchers now explore hybrid models that blend both approaches, suggesting that gravity might be slightly altered and that some form of unseen matter still exists. These mixed frameworks may one day bridge the gap between competing visions, proving that nature's truth is rarely singular. What remains certain is that the mystery of the unseen continues to guide physics forward. Whether through particles hiding in the dark or through a new understanding of gravity itself, the universe is still teaching us that visibility is not the same as existence. The unseen, whatever form it takes, still shapes the light. The universe may never have been meant to obey an either-or choice. As so often happens when humans try to box infinity into a single rule, reality resists the simplicity. Perhaps it is both matter unseen and gravity unrefined, substance and law sharing responsibility for the way the cosmos behaves. Yet for now, the balance of evidence tilts decisively toward dark matter. Its fingerprints are clear and persistent, in the bending of starlight around clusters, in the smooth growth of galaxies from early ripples, in the speeds of stars orbiting unseen centers, and in the faint relic radiation left from the Big Bang. Every dataset hums the same refrain: there is more mass than we can see. No single version of modified gravity has yet managed to recreate all of those clues at once. Still, those challenges have not failed. They have deepened the conversation. Each alternative forces cosmologists to refine their equations, to check for bias, to confirm that what seems certain is still supported by the evidence. Even when rival ideas fall short, they leave the science stronger. The dialogue between invisible matter and invisible rules keeps cosmology alive and honest. One side imagines a universe filled with hidden particles, the other a universe whose laws change their rhythm with scale. Both seek coherence in the same cosmic riddle. Perhaps, in the end, the truth will borrow from each, a universe that bends its rules softly while still hiding something beneath the surface. Whatever the final answer, the search has already given us something profound. Every equation scribbled on a chalkboard, every simulation running across supercomputers, every long argument under the dim light of an observatory adds a new stitch to the tapestry of understanding. Dark matter remains the leading explanation, carried by the weight of observation across space and time. But science moves, not only through what it answers, it advances through questions that refuse to settle. The persistence of mystery is not a flaw in our knowledge. It's the spark that keeps discovery alight. Every detour, every hypothesis that leads nowhere, still lights another small section of the path forward. And so, with the debate still alive, curiosity unspent, we can widen our focus. Instead of chasing one theory or another, we can step back and look at the grand composition itself. What is the universe made of? How do its ingredients, seen and unseen, fit together to make the structure we inhabit? From that distance, something quietly astonishing emerges. Everything we can observe, every atom, every planet, every beam of starlight, accounts for only about 5% of reality. The brilliant galaxies scattered across the night sky, the glowing gas clouds, the molecules that form living things, all of them together make up a sliver of the whole. The rest, the vast majority, belongs to domains we cannot see. Roughly 27% dark matter and 68% dark energy. In other words, the universe is mostly invisible, not because something hides it, but because its dominant forms exist beyond our senses. It's humbling to realize that the cosmic inventory is ruled by what we can't touch. The visible is the exception, the unseen, the rule. Imagine standing inside a cathedral so vast that its walls vanish into shadow. The shafts of colored light streaming through its stained glass are the galaxies and stars, the visible 5%. But the air filling that cathedral, the arches supporting it, the silent stone that keeps it standing, those are the dark components. They give shape to the beauty we can see. The universe's splendor lies not only in its light, but in the unseen scaffolding that allows light to exist at all. Dark matter forms about a quarter of the cosmos. It binds galaxies together and weaves them into clusters. It shapes the great filaments that stretch across hundreds of millions of light years, drawing a cosmic web that defines the universe's architecture. Without that quiet gravitational glue, space would be formless, a fog without structure, a sky without constellations. Beyond that lies the even deeper mystery. Dark energy, the substance or perhaps property filling nearly 2/3 of everything. Dark energy is not matter in any ordinary sense. It behaves as though space itself is imbued with a subtle pressure, a constant push that drives the expansion of the universe faster and faster. The galaxies are not just drifting apart. They are being carried on the breath of an invisible wind that accelerates with time. At first glance, these numbers seem abstract, but together they tell a story of delicate balance. The cosmos is not an empty void sprinkled with stars. It is a structured fabric, a composition where the unseen dominates the harmony. Every pattern we observe, the spin of galaxies, the clustering of matter, the rhythm of cosmic expansion, plays out against this invisible background. The dark is not absence, but presence. And yet, far from making the universe bleak, that dominance of darkness gives it grace. The luminous parts, the stars, the planets, the living worlds, are jewels set into an ocean of silence. The atoms that form everything familiar are the rarest material in existence. Sculpted from the residue of creation, we are made of that rarity, carried and shaped by the unseen. It's comforting in a way. The universe may be immense, but it isn't indifferent. Its emptiness is full of quiet purpose. The spaces between galaxies are not sterile gaps. They are fields where gravity and energy perform an ancient duet, balancing each other across nearly 14 billion years. Even nothing is not truly nothing. The vacuum seethes with energy, its fields flickering with virtual particles that appear and vanish faster than thought, Gravity curves it, light crosses it, dark energy stretches it. What we call nothing is the most fundamental something there is. Astronomers sometimes describe this as a cosmic inventory, a pie chart of existence where most of the chart is shaded with question marks. Only a narrow slice corresponds to the known and visible, yet those question marks are the reason the slice exists at all. The mystery is not a deficit, it is the context of all creation. The fact that we can measure those cosmic proportions so precisely, even without knowing what the components truly are, is one of science's quiet triumphs. Dark matter and dark energy remind us that ignorance is not a void to fear but a doorway to explore. They show that every answer leads to deeper questions, and every mystery uncovered expands our sense of wonder. Knowledge doesn't diminish the world, it deepens it. Future telescopes and instruments will sharpen this picture further. The Vera Rubin Observatory, the Euclid mission, and Nancy Grace Roman Space Telescope are being designed to map dark matter's influence with unprecedented precision and to measure how dark energy shapes the expansion of space. New detectors, new methods, new eyes on the sky, all will refine our cosmic map. But for now, we live in a moment of exquisite tension. We know the composition of the universe to astonishing accuracy, yet we don't know what most of it is. When you look up at the night sky, you are not simply seeing stars, you are seeing the surface of an invisible ocean. The galaxies are lanterns floating on that ocean, held in place by the currents of dark matter and carried outward by the slow exhalation of dark energy. The shimmering band of the Milky Way is a ripple on the surface of something immeasurably deep. It's tempting to feel small in such a universe, to think of ourselves as tiny sparks adrift in a vast indifference. But perhaps it's more accurate to see it the other way around. We are rare concentrations of visible matter, brief luminous knots of awareness rising out of the unseen. Through us, the universe has become conscious of its own shadow. We are the eyes and the voice of the cosmos looking back upon itself. That something made mostly of nothing can give rise to thought, curiosity, and awe is, in itself, a kind of miracle. The same forces that shaped galaxies have, through long chains of cause and effect, shaped the minds capable of wondering about them. Dark matter and dark energy are not merely background physics. They are the stage on which existence unfolds. The universe, as it stands today, is a fleeting arrangement in an ongoing story. The galaxies shine, the stars burn, the clusters hold together, but none of this will last forever. Even the brilliance of starlight is temporary, a brief flicker compared to the cosmic timeline. In the far future, when the last stars fade, it will be dark matter that remains silent, invisible, and patient, preserving the outlines of structure long after light has vanished. Dark matter is the quiet sculptor of cosmic architecture, and that architecture will endure long after its luminous tenants have gone to sleep. Stars will exhaust their fuel and die. Galaxies will dim into ghostly remnants, but the dark scaffolding that once held them will persist, vast and tranquil, like ruins standing after the civilization that built them has vanished. Over unimaginable spans of time, the universe's expansion will continue. Dark energy will keep stretching the fabric of space, pushing galaxies farther apart. The clusters bound by gravity will remain intact, but beyond them, the rest of the cosmos will drift beyond the horizon of visibility. The night will deepen, not in violence, but in distance, a slow dimming as everything recedes. In that far future, only the faintest embers will remain, the great blue stars will have burned out first, gone in cosmic instants. The small red ones will glow quietly for trillions of years before fading into black dwarfs, cold and invisible. The galaxies themselves will turn into silent, starless husks, their dark matter halos still intact, still defining the invisible boundaries of what once was. Eventually, the distances between clusters will become so immense that light from one will never reach another. Each cluster will be an island, surrounded by an ocean of silence. The cosmic web that once tied everything together will stretch beyond recognition. To any being that might exist then, the universe will seem strangely small, an isolated bubble of stars adrift in eternal night. Yet even then, the memory of structure will remain. The gravity of dark matter will continue to define the ghostly shapes of what once existed. The filaments, the halos, the skeletal framework of the cosmos will linger like the imprint of a dream. Even black holes, those final engines of energy, will eventually evaporate through Hawking radiation, fading away over timescales so long they defy imagination. In the end, only the dark matter particles themselves will persist drifting, solitary, too sparse ever to meet again, but still tracing the faint geometry of creation. It is not a tragic vision. There is no sudden end, no collapse, no explosion. The universe doesn't die, it rests. It exhales, unweaving the bright patterns it once wove. The structures formed by dark matter, the galaxies and clusters, dissolve so slowly that even time itself might seem to move differently. If one could stand in that distant age, orbiting a dying ember of a star, the sky would be dark beyond comprehension. A faint glimmer, perhaps a ghost of a galaxy, would shimmer like memory itself. The cosmic web would be gone, its strands stretched beyond reach, its music stilled. Yet even in that silence, the same laws would hold. Gravity would still pull. Dark matter would still weigh. Dark energy would still expand. The universe will continue, even without its light. And perhaps that is the deepest truth of all, that the story of brightness, of stars, planets, and life is only one brief chapter in a book mostly written in darkness. We live in a brief, golden interval, the bright middle pages of the universe's book. Galaxies still gleam, stars still ignite, and the night sky still glitters with the ancient shimmer of light crossing impossible distances. It feels eternal, only because our lives are so short. But this brilliance is temporary. Billions of years from now, those lights will fade, leaving behind the quiet geometry of dark matter, the silent lattice of gravity that will persist long after the last star goes cold. What we call the end is, in truth, only the universe exhaling, returning gently to equilibrium. From the cosmic perspective, there is nothing tragic in that fading. The universe has always balanced creation and dissolution, brightness and shadow. The same laws that allowed galaxies to form will allow them to dissolve. The glow will pass, but the structure will remain a record written in gravity's patient handwriting. The dark will inherit everything. It is the custodian of memory, the quiet architect of what endures. We tend to think of darkness as emptiness, as a void waiting to be filled. Yet in the cosmos, the opposite is true. Darkness is fullness. It holds, it cradles, it gives shape. When the final photon drifts away and the last ember cools, the universe will still be there, vast, patient, unbroken. And perhaps, just as stars once rose from the dark, something else may rise again. The universe is creative by nature. Its silence might not be an ending, but a pause, a breath between movements in an endless symphony. But that lies far ahead. For now, we are lucky. We live in the age of light, when galaxies still whirl in their luminous spirals, when nebulae still bloom in color, when the Milky Way still sweeps its pale ribbon across the sky. This is our chapter, our brief window to wonder. Darkness, throughout human history, has carried a reputation, something to fear, to chase away with flame or faith. Yet when we look closely at the cosmos, we find that darkness is not the enemy of light, but its foundation. Every spark, every star, every gleam of brilliance exists only because the dark made room for it. The invisible does not hide the universe, it holds it together. Picture the cosmos as a vast tapestry. The light is only the embroidery, delicate threads of gold glinting across an immense weave of shadow. The true fabric, the loom beneath, is dark matter. Across its unseen threads, galaxies are strung like beads, clusters hang like constellations, and the rhythm of creation hums in silence. Through this hidden structure, the universe found its form. Darkness is not absence, it is design. The story of existence, then, is not a struggle between light and dark, but a partnership. From the first fraction of a second after the Big Bang, darkness shaped the stage so that light could perform its brief and brilliant act. The stars we see are notes in a cosmic symphony written in a quiet key. Without the invisible accompaniment, their music would never have begun. The beauty of this partnership lies in its humility. The galaxies shining in deep space are breathtaking, not because they stand apart from darkness, but because they reveal what darkness can do. Every spiral arm, every radiant cluster is a sculpture carved by gravity's invisible hand. The universe is a gallery of unseen art, a slow, patient creation where the medium itself is mystery. And yet, that mystery doesn't frustrate, it comforts. There's peace in knowing that not everything must be illuminated to be real. The unseen world asks for nothing. It simply exists, steady and enduring. It invites curiosity without demand, a calm presence, like the surface of a lake reflecting both light and shadow without bias. Light owes its meaning to darkness. A sunrise moves us, not because it abolishes the night, but because it rises from it. The same is true of the cosmos. The blackness between the stars gives their shimmer its depth. Without that contrast, there would be no awe, no sense of scale, no silence to hold the song. Dark matter teaches that most of reality operates quietly beneath perception. The universe is not a roaring engine, but a tranquil sea. Galaxies drift, clusters turn slowly, and vast voids stretch between them in unhurried balance. The darkness does not rush, it endures, content in its stillness. Within that stillness lies a kind of cosmic grace. To study the unseen is not to conquer it, but to listen. Every telescope aimed at the sky, every detector buried underground, every sleepless scientist passing faint signals is performing an act of reverence. Science, at its best, is gratitude in motion, gratitude for a universe generous enough to still surprise us. The lesson of the dark is simple. Not everything must be known to be meaningful. The cosmos owes us no full explanation. It gives us glimpses, a glint here, a whisper there, enough to keep curiosity alive. That curiosity is our lantern, carried softly through the corridors of the unknown. To live in a cosmos made mostly of unseen matter is to inhabit a place where imagination and evidence overlap, We cannot see dark matter directly, but we feel its presence everywhere, in the movement of galaxies, in the shape of space, even in the fact that we exist. It is an invisible affirmation of connection. There is poetry in that connection. The atoms in your body were forged in stars, but those stars were shaped by dark matter halos. You are, quite literally, the child of both light and dark, your matter born in fusion's fire, your form guided by gravity's unseen web. To gaze at the night sky is to look into a mirror, the visible and invisible, working together to make you possible. When you stand beneath a clear sky and trace the Milky Way's arc, you are witnessing balance itself. Each spark of light tells a story of fire, but the darkness between them tells a deeper one, a story of patience and quiet strength. The stars are the melody, the dark is the rhythm that carries it. Perhaps the most beautiful thing about the unseen universe is its serenity. It doesn't compete with light, it enfolds it. The galaxies move as though in meditation, tracing paths set long before the first photon flared. The darkness doesn't ask to be seen, but once you understand it, you begin to feel it everywhere, not as void, but as the pulse of existence. Maybe that's why studying dark matter feels oddly peaceful. It reminds us that mystery isn't a flaw in our understanding, but an essential feature of reality. The unknown is not a wall, it's a horizon. It beckons us to keep walking, to keep wondering, to listen, even when the silence seems endless. The more we learn about the unseen, the more we realize we are part of it. The same dark framework that shaped galaxies also shaped the possibility of life, thought, and wonder. We are small, yes, but we are precisely the kind of smallness that can appreciate the vast. So let the darkness be a comfort. Let it be the cradle that holds the stars, the loom that weaves the galaxies, the silence that gives meaning to the song. In a universe where most of what exists is invisible, awareness itself becomes a form of light, not to banish the dark, but to honor it. The unseen is not something to fear, but something to marvel at, an infinite landscape of possibility, stretching beyond time and sight. The night sky reminds us that beauty does not depend on full understanding. Some truths live best in shadow, and as you sit beneath that same sky, remember that you are surrounded by the quiet architecture of the invisible, the framework that steadies galaxies, cradles stars, and gives shape to the night. We began by wondering what keeps the lanterns of the cosmos from drifting apart, and found our answer not in light, but in gravity's calm design. The picture, in the end, is simple. Light is the embroidery, darkness, the cloth. Close your eyes for a moment and return to that first image, a lantern suspended in a clear sphere. The glow is everything we can see. Stars, nebulae, the soft river of the Milky Way. The sphere itself, invisible but firm, is the dark that holds it. That is the universe we inhabit. Light singing because something silent keeps the rhythm. Darkness is not an enemy to be banished. It is the cradle of creation, the patient architecture that holds everything together.